Okay, the next alkylation strategy we're going to look at is pretty similar to the malonic ester synthesis. So just like with the malonic ester synthesis, we're going to start out with the overall transformation and then we'll dive into the mechanism. And again, we're going to start out with an alkyl halide or a tosylate, something like that. And our goal is, after multiple steps, to create a group that is now a methyl ketone. So the alpha position on the methyl ketone is right here, and our goal is to get this R group installed on that alpha position. So this is going to be an alpha alkylated methyl ketone. And the reason it's called a methyl ketone is obviously we've got a ketone right here, but on the other side, meaning the outside side, we've got this methyl group coming off, not an ethyl group, not a terbutyl group, nothing like that. All right, so we can make an alpha alkylated methyl ketone rather than an alpha alkylated carboxylic acid. And the mechanism is going to look a lot like the previous one. And we're going to start out with a different starting material this time that kind of halfway looks like the starting material we used in the prior synthesis. So in the malonic ester synthesis, we used diethyl malonate. Instead of using that, we want to make sure that we've got this methyl ketone functionality within our starting material. And this starting material is called ethyl acetoacetic. All right, and just like before, we're going to treat this with a base, and we want to make sure that our base matches our alkoxy group on our ester, right? We don't want to do any transesterification. All right, so we've got these two alpha protons, again, in between both carbonyls, quite acidic. So we can go ahead and grab one of these, and we can make our enolate, where we have a negative charge that is highly resonance stabilized. And just like before, we can do SN2 chemistry with this. So this is our SN2 reaction where our enolate can just attack this R group and kick off our leaving group, which is nice. However, like I said before, this R group can't be too hindered. So let's make a note that this should be primary or methyl. If it's a tertiary carbon, we're just simply not going to get any SN2 chemistry to occur. And just like before, we can get this R group installed off of that central position. And then, once we've got that done, all we need to do is treat this with some acid, dilute acid, and by doing that, we can interconvert this ester to carboxylic acid. I'm not going to go through that full mechanism because we already covered it during our carboxylic acid derivative chapter. And now we've got our carboxylic acid. But like I said, we actually can rotate this bond around. So I'm going to spin this bond, meaning this bond right here, and we're going to orient things a little bit differently. This time I'm going to have my OH group sticking up and my CO double bond kind of sticking out to the left. And just like before, we've got this intermolecular H bond, which is kind of neat. And what will happen under high temperatures is we'll get a decarboxylation to occur. And what that means is that this carbonyl is going to steal that proton. This bond is going to jump down, and then that bond's going to jump over. And this whole group, the CO2 right here, is going to get kicked off in the process. So we're going to get CO2 gas that will bubble out of solution. And then we'll end up with this enol. However, like we saw in our previous video, these enols very much want to go into their keto form. So we'll get CO2 gas as our byproduct, plus we'll get to our methyl ketone. And like I said, it's a methyl group because we can only have the CH3 group on here. We aren't going to have any other functional group. And in addition, we've got this R group coming off of the alpha position. It's kind of neat. All right, and like I said before, you can actually do this twice. So let's take a look at dye substitution. And with dye substitution, we again would start out with ethyl acetoacetate as our starting material. But what we do is we treat this first with our sodium ethoxide, and then we could treat this with our alkyl halide, and then we do this whole process over again with a different base. Oops, sorry, this should be step 3, not step 1. And then we would treat this with our second alkyl halide. And then in our last step, or actually, let's go ahead and show this intermediate. So we get both of these R groups installed. And then in our last step, we would treat this with our dilute acid and heat. And like I said, the acid's going to interconvert this ester to a carboxylic acid. And then the heat portion of this is going to blow off this CO2. And what this will do is it will leave us with a dye-substituted methyl ketone, where we would have 2 different alkyl groups coming off of this alpha position. All right, it is important to remember that you want to be judicious when picking these alkyl halides. And what I mean by that is typically you want to install your less bulky group in first. That way you're not making your next enolate super hindered. Super hindered nucleophiles aren't going to be good nucleophiles. So typically you want to start with your least bulky alkyl halide. All right, just for fun, I wanted to do this challenge problem. This challenge problem isn't necessarily the same as the problem we've seen above, but it's a combination of the malonic ester synthesis and some Claisen chemistry that we covered previously. My hint is that the product for this reaction is going to form a ring. So let's try to figure out what's going on, and we'll be careful and not go too fast. All right, so in this first step, meaning step 1, we've got ethoxide floating around. And when we think about this, we've got alpha protons here, and we've got alpha protons here. However, they're equivalent, right? This molecule's symmetric. The left-hand side's the same as the right-hand side. There's really no difference. And we can just grab one of them. Doesn't matter. So we'll go ahead and we'll show this. And we're going to get a nice enolate to form. And at this point, a lot of students are tempted to just immediately jump into step 2, right? And have this react with methyl iodide. But let's wait. Let's ask ourselves, is there anything else we can do with this? And the answer is yes. Before this has a chance to react with methyl iodide, it can actually attack itself. And that's what's going to form that ring that I gave you the hint about. All right, so let's figure out what's going on here. And I like numbering this. So I'm going to say 1, 2, 3, 4, 5. So it looks like we're going to make a ring of 5 carbons. So I'm going to go ahead and show that ring. And I'm just going to number it however I want. And off of carbon 1, we still have this entire group. So I'm going to go ahead and plug that group into carbon 1. We've got that CO bond, and we've got this ethoxy group. So we've got that accounted for now. And then over on carbon 5, what we have is an oxygen with a negative charge, and we've got our ethoxy group. All right, so let's take a look at what would happen next. Well, as we saw in the Claisen reaction, this could go, clamp down, and kick off ethoxide as a leaving group. So that seems to make sense. So let's go ahead and draw this over here. and ethoxide was kicked off as a leaving group. Again, a lot of students are tempted to stop here. But if we think about it, we've got an alpha position right here that's in between two carbonyls. That means that this proton, it's right here, is going to be really acidic. So we can go ahead and grab this alpha proton and we can make our enolate. So the product after step 1 is actually going to be both a new ring and it's going to be this resonance stabilized enolate. However, after this step, there's really nothing more that we can do. It's not going to attack anything else. There's no other acid-base chemistry that can occur. So we're kind of stuck here after step 1. That means that we can jump into step 2 now. And with step 2, we've got this methyl iodide. And the methyl iodide can now alkylate that alpha carbon with the negative charge. So we can go ahead and we can draw this in. And I'm just going to go ahead and draw this as a CH3 group. Let me clean this up a little bit. I don't like the way it looks. And there we go. So now we've got the intermediate from step 1. I would say at this point there's nothing more we can really do with this except make my molecule look a little prettier. All right, so now we're done with step 2. If we go back up and look at our list of reagents, our last step is to treat this with acid, and I also forgot to include heat. So let's try to figure out what happens with acid and heat in this last step. Well, if we have dilute acid, we do know that esters under these conditions will interconvert to a carboxylic acid. So let's go ahead and figure out what would happen then. So now we would have this carboxylic acid kind of hanging out over here, and we would have this ketone. Sorry, it's not easy drawing these sometimes. And now we're ready to go in the next step. In the next step, what we're going to do is apply the heat. And just like before, we're going to get this intramolecular H bond to occur. And this is going to jump up right here and steal that proton. The bond between the hydrogen and oxygen right here is going to swing over. And we're going to kick this bond down right here. So really, this entire carboxylic acid group, in fact, let me change all my colors there. This entire carboxylic acid group is going to decarboxylate, and we're going to kick this off as CO2. All right, so we're almost there. We've now got a double bond here. We've got an OH group here. We still have this CH3 group coming off of that top carbon, and we've kicked off CO2 gas. All right. At this point, though, we're left with an enol, and we can go ahead and tautomerize this enol all the way to our ketone. So we can go ahead and show this enol going to a CO double bond, and we can get our final product here. And like I said, CO2 is going to be our gas. So in this entire mechanism, we are actually able to make an alpha alkylated ketone. So this would be our final product for this reaction. So I know these look kind of scary, but as you can see, these are really versatile reactions, and you can sometimes combo these Claisen condensations and alpha alkylations together to make these pretty intricate products. It takes a while to practice. These are very challenging, but I would encourage you to go through your book and do some of these challenge problems. All right, good luck studying.